All right, now we're going to do Physics 2. So again, this is Form J, the only one that gets released. This is the form that a lot of the Eastern time zone in the US takes. Unfortunately, they don't release all the forms. As much as I would love to do 16 of these, we only get Form J. So if you had a different form, you might think your questions were harder, and they could have been, but they're all graded on different curves. So if you had a harder form, the scores are adjusted, like the cuts at least, to account for that. So without further ado, we'll go. I thought this was pretty standard. No optics or waves, which was interesting, but very normal things that were asked. Like, I don't think any of these questions were really strange in any way. So here we got a gas. Obviously, this is thermo, right? So a sphere is in thermal equilibrium with a gas. It starts at the state in a sealed container. We then heat the gas and send it to a different state. So originally, we have n moles at a pressure P and a volume V. And we're ending with the same number of moles, but the pressure is increased due to the heating. So we know that our temperature is going to increase during this. So first, we actually want to sketch a possible curve showing the distribution of atom speeds after the heating process is completed. So we know that the average kinetic energy is going to be proportional to temperature. That is what temperature is. It's a macroscopic visualization of this microscopic kinetic energy of each of these atoms. So this means that on average, an atom will be at higher speed in the second state because temperature goes up. But they're the same number of atoms. So we can't just do something, oh, that's an awful peak, but we can't just do something like this because that would mean that there's more atoms in the container. So what we have to do is we know that more of the atoms would have speeds that are higher, so like over here somewhere, but also that means more speeds are possible out there. We need to show that the number of atoms stays the same. So I really think the 2 points are just going to come from making a flatter graph whose peak is to the right of the original peak. So, because again, by having a higher temperature, that means more speeds are possible. So the curve is going to extend higher in regions out here. But it had to get flatter because we had the same number of atoms. So this is actually not the easiest thing if we forgot how this works. So A1, point A1 is probably making a peak or a curve that shifts to the right. So peak shifts right. And then A2 is for a flatter curve. And I'm sure that we're objectively defining flatter as your second curve cannot touch this line. So any curve whose peak is to the right of the vertical dash and whose height is below the horizontal dash gets those 2 points. That's kind of interesting. I thought this did a good job of like making you deal with some representations that aren't the most common. Derive an expression for the change in temperature of the gas in the heating process. Well, we got temperature, we got moles P and V, whatever it could be. Well, obviously it is ideal gas law. So we got PV equals nRT. And if we're interested in the change in temperature, delta T, it might be helpful just to get the temperature. So the temperature of the gas would be PV equals nR. So our initial temperature would be, we'll check our volumes here. Yeah, it looks like there's no subscripts. So our initial state was at pressure P, volume V. And our final state was at pressure 3P and volume V. So this means that our delta T is just going to be our final temperature, 3PV over nR, minus our starting temperature, which is PV over nR. And we see that there's our common denominators, so we can just do 3 minus 1. So that's 2 PV over NR. Now, I do know that, like, there's a much easier solution, like a one-liner. You could just do, since P is constant, you could have just said, like, P delta V equals NR delta T, with delta V being 2V, and solve. Like, that totally works. I don't know if that was the most obvious thing you could do, though. Usually this derivation is worth 3, so you probably got a point for the ideal gas law. So that's going to be A3, because we're still in part A. You probably got a point for solving for the temperature in the final state, A4. And then a consistent delta probably got you A5. So now what's happening is we're transferring heat to the sphere in this process. So there's a sphere at the bottom of this container that is being heated by the gas. So it also tells us the amount of heat transferred to the sphere was Q. Well, we have Q, we have delta T, we want specific heat. Well, specific heat, it's always just Q equals MC delta T. So that means C is equal to Q over M delta T. And we just substitute our delta T. So Q was QS, M is M, delta T was 2PV over NR. And you could simplify if you wanted to. QS NR divided by 2 MPV. That's a lot of letters in there. I imagine it's just a point for the setup and a point for substitution. Now for our B part. An insulated container is filled with a liquid. The liquid has a greater mass than the sphere, and it has a greater specific heat than the sphere. They exchange heat, and equilibrium is reached, and we have to compare which one of the two objects has a larger temperature change. Now, I actually got a comment about this, that, wow, your FRQ about specific heat really prepared me for this. So my Physics 2 practice exam, this scenario, or something a lot like it, was my QQT, where we had to reason about how temperature change is influenced by specific heat. So we know that anytime a closed system exchanges energy, we have the same energy transferred. Because if heat is transferred to one object, well, it had to come from the other one. So the Q is always the same in these isolated systems. And it says that the sphere has less mass and the sphere has a lower specific heat than the liquid. So we should definitely start by just doing a justification, because we know that this is a closed system. So Q equals MC delta T is the same for each object. Should put some absolute values there, because technically heat is lost from one and gained by the other. So for the liquid, M and C are larger. So since Q equals MC delta T, if M and C increase, then delta T must decrease for the same Q. So all that is to say that the liquid experiences a lower temperature change. So the sphere must have a larger temperature change. So why this connects to my problem is you can say that specific heat is like thermal inertia. So the liquid, even if the masses were equal, the liquid has more specific heat, meaning it is harder to change the temperature of the liquid. So if you put the same agent of change or the same cause, which is your energy, into the liquid, it's not going to change as much as the sphere. And also, you can think of the case of like the sphere having much, 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 much less mass or specific heat, and it would just sort of instantly come to the liquid's original temperature. You can always earn the justification points even if you pick the wrong one. B1 is the checkbox. I am almost certain B2 is going to be saying the heat transfer is the same. And something about the fact that for a fixed Q, M and C going up must mean that T has to go down to create that same energy transfer. I'm sure there's other explanations to this, and you can run those by me as well. This is just the most obvious one to me because I wrote a problem like this earlier. So I thought that was a pretty standard thermo question. All right, so modern physics on the TBR. I don't know if I would have expected this, but it's actually a pretty good question. So we have like our potential energy states available in an atom. And we first want to draw sort of the possible transitions we can get that result in an emission of a photon. So the energy of an absorbed or released photon has to be equal to the delta E of the transition by energy conservation. So if we're looking to emit a photon, that must mean that we're going to an energy level state that is going to be lower. So, for example, if I go from 2E0, negative 2E0 to negative 3E0, well, that would emit a photon of energy plus E0 would be the photon energy released. Then I could also go from 2 to 1. And that would release a photon of energy, well, 3 to 5, that's 2 E0. And then lastly, I could do like the big jump from 3 to 1, and that would be an energy difference of positive 3. And it makes sense that if we go the biggest jump, that emits the photon of the largest energy. So I actually find it interesting. We have to figure out how to assign 3 points to this. Now, I think you probably get a point for like the 3 to 2 and the 2 to 1 transitions. Maybe you get one for finding like the cross transition 3 to 1, like the stair step skip one. And then your third point, I'm almost certain there's a point for like all arrows point down. Because the transition probably has to have a direction to it. And you have to show that it's only the going to lower potential energies that's releasing photons. So I don't think doing something like this would give you that. Because it's really specific. It's about the emission of a photon. Derive an expression for the highest energy photon that can be emitted from the atom in terms of E0 and physical constants only. Well, highest energy is going to correspond to highest frequency. Frequency, that's how you spell that word, which corresponds to the lowest wavelength. So this looks like modern, but really this is mostly a waves question. So I actually see why this is asked, because you get to hit a lot of the waves questions on here about wavelength and frequency. So we know that the energy of a photon is equal to Planck's constant times the frequency. So what is the highest energy photon we can emit? Well, if we go from our our greatest difference in energy levels, that's going to create the largest energy photon, right? Because it's the biggest step apart. So 3E0 is the largest possible. Planck's constant is Planck's constant. And then since we know that for electromagnetic radiation, we know that the speed is equal to lambda f, and the speed is the speed of light. So we can just replace frequency with c divided by lambda. So this would mean 3E0 lambda is equal to hc, or lambda is equal to hc over 3E0. And again, that should qualitatively make sense, because if I have a larger energy, I'm going to have a lower wavelength. So you probably got a point for identifying the highest energy state. You probably got a point for substituting c over lambda for frequency, and then you probably got a point for the correct answer. Oh wait, this is 4. This is 4 points. You probably got a point then for the Planck, the energy of a photon formula. All right, now it did give us some extra info that it said we have a device that can emit monochromatic light of all these different wavelengths. So this is not about the atom, this is about a device that can emit any wavelength of light it would like. And it says that photons with a wavelength lambda 0 have energy 4E0. And we need to plot a curve for the energy of the emitted photon as a function of the wavelength. Well, we said that E is equal to HF, which is equal to HC over lambda. So this is a reciprocal function. So notice what this means is that if I double the wavelength, for example, then I'd half the energy. So this also means like the product is going to stay constant of E and lambda, because E times lambda would be a constant. So we actually have a grid line, so they will score you on the grid, I imagine. So if we double the wavelength, we have to half the energy to make the product of grid boxes constants. And then if you double it again, you half the energy again. So we get a curve, because this is about a device. This isn't about an atom. So we're assuming we get an entire continuous spectrum here. So you would probably get a point for concave down. You'd probably get a point for... Do you get a point just for correctly plotting one of the points? That seems a bit free. Maybe though. That lambda of 0, 4E0 is on the graph. C2 you'd probably get for the other points. You'd have to say that like 2 lambda 0, 2E0 is on the graph, and 4 lambda 0, E0 is on the graph. And 3 is concave down, maybe. Again, I'm just speculating. That's how I would assign points if I had to get 3 out of this. And then a student claims that based on figure 1, the atom can emit a photon of wavelength lambda 0 and energy 4E0, like shown here. Is that possible? So the student claims we can emit an energy, a photon energy at 4E0. No, we can't. We showed them all. So the student's claim is incorrect, because the highest possible energy change is n equals 3 going to n equals 1, which is 3E0, which is most notably less than 4E0. So you say the claim is incorrect, or correct, I guess. I can't really find a scenario where it's correct if you draw wrong like A, because it gave you the, I don't see how you get 4E0 out of that. And then D2 is correctly comparing like the highest energy transition to 4E0. So since 3 is less than 4, you can't do it. All right, now we got a lab. This is actually like 2 non-trivial labs here. I like it. These could fly for APC, E&M. Experiment 1, students want to find the magnitude of a B field between plates. We have a device that sends undeflected ions in a straight line next to a motion detector. Well, if you're moving in a straight line between charged plates and a B field, we know it's a velocity selector. So to determine our experiment, sometimes it's best just to write the equation, right? Because we know that there's going to be balanced electric and magnetic forces. Magnetic force is QVB, electric force is QE. The charge cancels, so I get E is equal to VB. But it actually says we don't have that. It says instead we have a variable power supply. So the motion detector gives us speed. We want the field, the B field. So we have to relate the electric field to this potential difference, script E. So we also know that for uniform fields, we can say that delta V is equal to ED. So this means our potential difference, script E, is equal to ED, or the electric field is equal to E over D. And I don't really like fractions, so I'm going to say that the potential difference is VBD. Oh, look at that. I've seen that before. So this is sort of the Hall effect. It's not the Hall effect, but it's the same equation for similar reasons, because you have electric and magnetic forces balancing each other. So all we have to do for our experiment is, it says the charges are shot out at a known velocity v, so that's known because the motion detector can do that. The plate distance is known, so we're going to find the v for different batteries. So this is how easy it is to get your lab points. So we measure the power supply EMF, then we measure the undeflected speed, and it says we already know the plate separation D. So then to get our uncertainty point, we just say repeat for multiple values of the EMF, measuring the undeflected speed each time. There's only one speed gets you through the plates, undeflected. All right, how do we graph it? Well, we came up with this equation. We came up with this equation that the EMF between the plates is V times B times D. So I can earn both B points just by saying the EMF is one of our variables. It's going to be our Y variable. And the other variable that we changed, just to make it easier, we're measuring the speed. I'm just changing the order just so it's easier to put like my speed V in a box. And then that means that my slope is just going to be the number in front. This does earn both B points. I didn't actually have to solve for B. I could just say the slope is B times D. Of course, there's lots of other ways of doing this experiment and setting up the linearization. As long as it's linear and you're consistent, you'll get the points. Like graph EMF over plate separation versus V. The slope is B. Like that works. I imagine that's a common one. All right, now we have the mass spectrometer. This is another pretty standard scenario with magnetism. So we send spheres at known speed, we measure their radius, taken for different B's. So anytime you see the mass spec, we know it's going to be a magnetic force is supplying a centripetal force. So the QVB, magnetic force, causes you to go in a circle via mv squared over r. Or we'll use lowercase. One of the v's goes away, so we get QB equals mv over r. So QBR equals mv. So r equals the standard result mv over QB. This was a multiple choice question of mine for sure. This shows up all the time. You didn't have to do a lot of deriving. This is usually more derivation than is required on the lab. But this is a pretty standard one, so it's fair game. So how do we linearize given R and B? Well, R lives in its own box already. That's cool. So I can just graph R. And then M is a constant, V is a constant, 1 over Q is a constant, but 1 over B is not. So this does require linearization. So that means the slope of my best fit line will be mv over q. V is given. Q is given. M is what we want to find. So, blah, blah, blah. Insert off-camera mining joke here. Here's the linearization. So, to get your C points, C1, you have to have picked a linear relationship. We don't care what relationship you graphed as long as it's linear. So some sort of reciprocal has to work out here. C is the scale plus the units. So make sure if you transformed anything, you transform the units as well. C3, you got to plot the points. And C4, you needed to do the best fit line. So even if you graphed something that's totally not linear, you get C2, C3, C4, as long as you committed to scaling the axes properly, putting correct units on your axes, plotting the points, and best fit lining. Now, Desmos gave me this regression equation. So we don't care how you get the slope. You could totally just rise over run it, and it's probably good. To get D1, you have to say, what is my slope equal to? So I actually earned D1 up here when I said my slope relationship, but there's D1. I said my slope is mv over q. I earn D2 by doing all of this lovely algebra to get approximately this answer. I have no idea what the range is. If it's somewhat close, you probably got it. They try to be really generous with the range here. We don't want it to be like a grid line counting contest. Like, if it's close, it's close. But this is what it should work out to be. All right. Now, this is a nice and short QQT. It's about equipotential lines. So we have a sphere that moves to the right at S. And then it goes to T. We want to figure out if the speed increases, decreases, or stays the same as it reaches T compared to what it was at S. So what do we know about equipotential lines? Well, we know that E points downhill. We're also given that this is a positive charge. So field is always perpendicular to equipotentials and it points downhill. So downhill and perpendicular would look like this, because negative is, of course, downhill from positive. So it looks like we just have an E field that is going to just point to the left on the line connecting the two charges, or two locations, rather. And we know that we have a positive charge. So this positive charge is going to get slowed down because we know that F equals QE. And we know that positive charges accelerate along E field. So this was my initial solution I thought of for the QQT. I don't know if this is the most common one because there's a really easy one that I'm actually going to write up. But my solution was the E field points downhill, so the E field points left throughout this entire region. Positive charges accelerate along the E field, so there will be a force against the positive charge's velocity, causing it to slow down. So it slows down at t. Its speed at t is lower. Now here's a much simpler solution. I'm sure you get points for like, so the checkbox is A1, and then the independent points you could get for the justification. You probably get a point for saying something like this, or like correctly identifying the direction of the electric field. And then you get a point for saying that positive charges feel a force or accelerate along the E field, something like that. But here's actually the more simple solution. Is anytime you talk about speed in E&M, it's probably energy related for electrostatics. So we could say that the potential energy of a positive charge is equal to QV. And we see here that the potential energy, or the potential decreases. So the potential, or sorry, increases rather. The potential increases from S to T. So this means delta U, which is equal to Q delta V, is positive. But since energy is conserved, delta K is negative. So the speed at T is lower. So if you did this approach, I imagine you get a point for saying like the potential increases if you go from S to T. And then you probably also get a point for saying something about like energy conservation, where if potential energy increases, kinetic has to decrease and so on. This is definitely the simpler solution. I personally always think about the E field pointing downhill. That's kind of just how I initially teach these equipotentials. So that's why this was my first approach, but energy approach is probably the least amount of writing you have to do. All right, what's the kinetic energy at T? Well, our second solution makes this really easy because delta K is negative of delta U, which is equal to negative of Q times delta V as we go from S to T. So from S to T, the potential at T is positive 2V0. The potential at S is negative 3V0. So I end at positive 2V0. And I started at negative 3V0. So my change in kinetic energy is negative Q times positive 5. So that would be negative 5QV0. And what is delta? Well, delta is just final minus initial. So final kinetic minus starting kinetic is equal to negative 5QV0. So this means my kinetic energy at the end is equal to my kinetic energy at the start minus 5QV0. Or using their variables, the kinetic at T is the kinetic at S minus 5QV0. So notice this is consistent, right? Because it says our kinetic energy will in fact decrease because Q is positive. So how do you get points? Here's your B3. This is your answer point. I imagine this is a point. Delta K is minus delta U, something like that. Energy conservation. And I'm sure you get a point for like the potential difference between the 2 points, probably. Then it says we replace this positive sphere with a negative sphere. Does this increase, decrease, or not affect the kinetic energy? Well, the new kinetic energy at T is bigger. And it says we must use our derivation in part B. So we see that because if we have a negative, well, negatives, we know negatives will do the opposite as what a positive will do. So if the speed decreases for a positive charge, it must increase for a negative one. But it wants us to use this expression. So if Q is replaced by negative Q, then K new would be equal to Ks plus 5QV0, which is larger than before, which is greater than the original value of KT. So that's pretty standard. I thought that was a neat one. It's not often we see equipotentials as an FRQ. Sorry, I'm going to keep my system here. So I think the C2 point is going to explain that like addition and subtraction signs are going to reverse. So something about the sign reversal. It's a C2, I bet. Yeah. I thought Physics 2 was very fair. This had good coverage of a lot of the curriculum as well. So I liked this. I actually had a lot of fun doing this set. Just wish there were more of them to do.